Next, in part 2, let's look into the resolution rule and how it's applied in propositional logic. The resolution rule, or the resolution method, was proposed in 1965 by John Allen Robinson, and it was one of the more important moments in the history of AI. There is one rule actually that makes up the method, the resolution rule, defined as this, or in horizontal form as this. Now, the rule takes two formulas as input, A or F, and not A or G, and gives F or G as a deductive consequence. The rule actually at first glance looks quite strange. One thing that can help you to memorize, to remember what the rule does, is to think as the rule of doing cancelling out of the atoms that are of the opposite polarity. So we have an A here, a non-A here, and what the rule essentially does, cancels these two atoms, and what we are left with, the OR F and OR G part, are combined to give us the deductive consequence. So again, A and non-A are cancelled, and F and G are brought together to give us deductive consequence. Two remarks here. First, the rule is actually quite peculiar and picky in the sense of what it expects to get as input. The two clauses have to be of the form of a disjunction of literals, atoms or their negations, and the deductive consequence is going to be a disjunction as well. So that's one first thing to note. The other thing is, of course, the question of soundness. Is the resolution rule a sound rule? It has to be, right? We'd like the rule to be actually sound to give us the logical consequences. So the question then is F or G actually the logical consequence of these two premises? So does this relation hold as well, in addition, to the deductive consequence relation? We'll look into that, and I can tell you already now that the rule is sound, obviously, otherwise it wouldn't be that famous and so widely used. And we'll prove this on the next slide. But before we do so, let's try to reason about the resolution rule in a slightly different way by reframing the rule in terms of the rules of natural deduction. I can do this by essentially rewriting the formulas, the premises as follows. A or F is actually equivalent to not F or G, which is equivalent to not F, sorry, not G, this should have been an A, let's go back, or A, which is equivalent to F, sorry, not F implies A, right? And that's one premise here. The second premise can be rewritten in terms of A implies G. Okay, so you see the two premises here, A or F, and not A or G are actually equivalent to not F implies A and A implies G. And now I can refer to the syllogism rule. It's one of the rules from the set of natural deduction rules, which essentially tells me if I have A implies B and I have, B implies C, then this is entailing A implies C. Sort of like a transitivity rule, so to say. So if I apply the syllogism rule in this particular case with, these two premises, what I get as a result is going to be not F implies G, not F implies G, which again I can rewrite. And if I do this, this is equivalent to not F or G, which is equivalent to F or G. And that's exactly the deductive consequence that the resolution method is giving me, right? So you see, I can actually relate the resolution rule to the rules of natural deduction which by the way are sound as well. So that's sort of one way to prove the soundness of the resolution rule by referring to natural deduction rule. Uh, but let's do this in a more proper way, in the sense of independently of the other deduction methods. And in order to do this, we actually need to prove that what the resolution rule is giving me as a deductive consequence is indeed a semantic consequence of these two premises, right? And the way I can do this and should do this, since this is a semantic relation, keep in mind, whenever talking about semantics, we need to, in case of propositional logic, we need to do truth tables. So we need to prove that, whenever these guys here, these two formulas are true, the deductive consequence is true as well, and this then means that it's actually a semantic consequence as well, right? So let's do the direct method. We have 1, 2, 3 variables in play here, so it's going to be 8 interpretations. Here I have the 8 interpretations, and what I do next is I construct the truth values across these 8 interpretations for all the both premises, and then I combine them, the two premises here. I also compute the truth values for the deductive consequence here and construct the implication, right? Is it the case that if the premises are true, this implies R, the deductive conclusion, a deductive consequence, and it turns out this implication is always true, so it's a valid formula. And then by the definition of logical consequence, I actually was able here to prove that this thing here is the logical consequence of these two premises, which then by the definition of soundness makes the resolution rule a sound rule. Okay, that's a good thing. So resolution is sound. So resolution is a sound rule, and another cool thing about resolution is it's a single rule, and this will make implementation easier. But before we actually look into that, let's go back one step here and talk about the input to resolution. We mentioned earlier that resolution is actually quite picky when it comes to what it expects to have as input, as the premises. It needs to be a disjunction, right? Now, since resolution can only be applied to premises that are disjunctions, this raises the question, is this actually a restriction here, or is it not? It turns out it's not. We can rewrite any formula of propositional logic as a disjunction of literals, and this form is going to be called a clause. So a clause basically is a disjunction of literals. Let's first define the clause, and then I'll show you the procedure which will turn your formula, whatever formula, into a clause. Okay, so a clause is basically a thing like this, a disjunction of so-called literals, and the literal is an atom or its negation. If I end up with just a single literal, then this is going to be called a unit clause. So a clause with a single literal. Here are examples of literals. All these things here are literals, atoms, so they're negations. And here are examples of clauses. A or F is a clause, not A or G is a clause. And here we have one long clause. Notice here that I am dropping the parentheses. So technically and formally, this isn't the well-formed formula, since I would need to have parentheses around the or terms. But since the or operator is associative, then actually it doesn't really change a thing in terms of interpretation. So I am allowed to drop the parentheses when I'm writing down the clauses. And yeah, the last example is the formula F, which is a unit clause. So a single atom is a clause as well. Okay, now that we know this, let's define a resolution first in a more general terms by looking at clauses of variable length. So what the resolution rule does is it takes one clause here on the left hand side and another one on the right hand side here. The clauses can be of different length. So let's say the first one is of length n and the other one is of length m. That's the number of literals, right? And what the resolution rule does, it identifies two literals which are of the opposite polarity, that is complementary literals. So one is the negation of the other, otherwise they're the same. And what it does, it will cancel these, and the result, the deductive consequence, which is called a resolvent, is a disjunction made of the remaining parts from both input clauses. Okay, so notice here that fi has been skipped here and gi has been skipped as well. Okay, so that's what resolution does to input clauses. Let's look at a couple of examples. The first example, this is my first input clause, this is my second input clause. What I can do here with the resolution rule, I can resolve or cancel the B and not B literals. The other way of saying this is I'm resolving on the B atoms or literals. And what I end up with is A here, not C from the first clause, and D or A from the second one. And if I put them together, that's my result. Okay, so that's the first example. The second example is a clause not A or B, and the second clause is A. A is gonna be cancelled. What I'm left with is B from the first clause, nothing from the second clause, which leaves me with only B from the first clause, and that's my deductive consequence. By the way, notice that this is actually modus ponens, what we are doing here. Okay, the third example is an example where I'm cancelling the B literals here. I'm left with A from the first clause and A from the second, which when combined gives me A or A, which by the way is equivalent to A as per factorization equivalence. And the last two examples, it's the same input for the last two examples. What they showcase here is that I can resolve or cancel the A literals here, or I can do this for the B literals here. So in case I have options, if there is more than a single pair of complementary literals, then I can do different derivations, different deductions. In the first case, I end up with B or not B, and in the second case, I end up with A or not A. Now, notice that in both of these cases, the semantic value of these deductive consequences is that it's actually a tautology. That both formulas are always true, right? It's B or not B and A or not A, which basically means I was able to derive a tautology, right? Notice that the resolution is a sound rule, so I'm basically saying here, okay, the tautology, a valid formula, is a logical consequence of these input formulas. And then recall from our discussion from last week that this is actually always the case. It's always the case that for any given formula, the tautology is its semantic consequence, since by the definition of logical consequence, which basically asks for whenever this is true, this has to be true as well. Now, this one is always true, so it trivially follows that a valid formula is a logical consequence of whatever formula. Now, in practical terms, what this means is, these deductions here, these derivations don't really make much sense because we know they hold anyway. So later when we talk about different strategies for doing resolution, we'll actually want to avoid the cases where the deduction ends up being a valid formula. Okay. Now let's go to the issue of converting a formula to a set of clauses, right? So if the premises need to be clauses for the resolution rule to be applicable, then I guess the first question is, does this in any way restrict the application of resolution? It turns out, as I said, no, because every formula in propositional logic can be represented as a conjunction of clauses. And the way to do this is to convert the formula into a so-called conjunctive normal form. A conjunctive normal form basically means that I will have formulas conjoined with conjunctions, right? And each of these formulas here internally will be a disjunction of some literals, right? So it's conjunctions as the outer operator and disjunctions as the inner operator. That's called a conjunctive normal form. The dual form to the conjunctive normal form is the disjunctive normal form, where you would have the or operator as the outer operator and the and operator as the inner operator. And I guess you're probably familiar with the disjunctive normal form from other courses. But here we are now after the conjunctive normal form. If I'm able to get to the conjunctive normal form, then each of these elements in the conjunction is actually a clause, right? Since the clause, per definition, is a disjunction of literals. Okay. So let's look at the procedure here, how we can convert the formula into conjunctive normal form. But before that, let's define what the conjunctive normal form is. So formula F is in a conjunctive normal form if and only if F is in the form of a conjunction of subformulas F1, F2, and so forth, and Fn, where each of these Fi's is actually a disjunction of literals, where literals are atoms or their negations. Okay, now that we know all that, let's try to convert a formula, whatever formula, an arbitrary formula of propositional logic, into conjunctive normal form. And this can be done in 4 sequential steps. The first step is that we eliminate the equivalence operator here by essentially using this equivalence here and replacing equivalence as a logical operator with this formula. Okay. After we're done with this part and we have eliminated all the equivalences that there are in the formula, next we look into implications. We'd like to eliminate implications, which we can do by using the equivalence that an implication is equivalent to not F or G. Okay, and then we repeat this until we got rid of all the implications. Then in the third step, we move negations so that they are next to atoms. Since in a clause, negations have to be close to atoms to make literals, we need to apply the De Morgan's laws to basically push the negations onto atoms, right? So in case the negation is here in front of a disjunction, by the De Morgan's law, it's going to be switched to a conjunction, and the negation is going to be put in front of the atoms. And in the opposite case, if the negation is in front of a conjunction, I'm switching to a disjunction and negating both atoms. Okay, that's the third step. And finally, in the fourth step, I will be applying the distributive law to convert a disjunction of conjunctions into a conjunction of disjunctions, right? So notice in this case that this is exactly the opposite of what I want to have. Since conjunction is the inner operator and disjunction is the outer operator, I need it to be the other way around, and therefore I am applying the distributive law to get this. Okay. The idea is that you can actually convert any formula into CNF by following these 4 steps. There's 2 things that you need to take care of. First is to repeat each and every step, each of these 4, for as long as there is anything to to be done. You repeat the equivalence elimination until you're done with equivalences. Then you move on to implication elimination until you're done with all the implications and so forth. And another thing to note is that whenever we have double negation in front of an atom, you'll be replacing this with the atom, right? By basically applying the involution equivalence. Okay, let's convince ourselves that this actually works by looking into an example. So the example asks us to convert into the clausal form this formula. The formula is obviously not in a conjunctive normal form. There's an equivalence here, implication as well. So let's see what we can do about this. The first step is to eliminate the equivalence by replacing it with an equivalent expression. Okay, that's taking care now of the equivalence. The next step is to take care of the implication, right, which is here. And by the way, I also removed the double negation, right? Now, to eliminate the implication, I'll rewrite this as not antecedents or consequent, right? And here I am. The next step is to move the negations in. So there's one negation, but it's actually, the scope of the negation is two atoms, and I need negations to be next to atoms. So what I'm going to do here, I'll be applying the De Morgan's law, and this will get me not C and not D, right? Not C and not D. Here I am. Okay, so this is what I'm left with after step 3. And now in step 4, I need to apply the distributive laws to convert the formula to a conjunction of disjunctions, because what I have here, what I've got after the third step, is actually not a conjunction of disjunctions, right? Because the OR operator is the outer operator and AND is the inner operator, and here's one AND operator here. So what I'm going to do is I am applying the distributive law to distribute this over the OR operator, this, so that's my first combination here, and this, that's my second term here, right? And then, I realize I'm still not done, since I've got conjunctions. Here's one, here's another one as the inner operator. So I will need to apply distributive law once again, twice, like here and here as well. And after here, 2 more steps, I'm actually done, and this is the final conjunctive normal form, where indeed I'm ended up with a formula where there is conjunctions as the outer operators and the OR operator as the inner operators, and the negations are next to atoms. Okay. Now, this actually is the CNF, and now to obtain the clauses, that's just the matter of removing the AND operators and treating these 4 guys here as four clauses. So a CNF formula can be represented as a set of clauses where we implicitly assume that there is an AND operation in between them, and then in turn each clause can be represented as a set of literals where we implicitly assume that there is an OR operator between them. So I'm basically saying that this formula, this is the result from the previous example, can actually be represented as a set of sets, where we basically say that the operation between these elements here is an AND operation, and the operation between the elements within a subset here is actually an OR operation. I guess when you do this in code, this would be like a nested list, a list of lists, or maybe a set of sets, right? Typically, when we do inference manually, then we'll actually prefer this form where we write the clauses one beneath the other. And implicitly, so we explicitly have the OR operator written down, but the AND operator is actually implicitly assumed to hold between the clauses. And that's the form we're going to use most of the time. Okay, now that we know all that, we can put all of this together into the resolution algorithm, a very simple one, which basically starts from an initial set of clauses, which we obtained by, taking a formula here and doing the conversion into CNF, right? And, once we have this set of clauses, we will apply the resolution rule on a pair of clauses that we can actually resolve because they have complementary literals, right? And then we'll look into, have we actually reached the end? Is the termination condition satisfied? And there is two things that can actually happen here for me to finish. The first is, okay, I derived what I wanted to derive, so hence I was able to prove the deductive consequence, or I haven't, and in this case, what I've just derived, that's not the final thing. What I've just derived, I'll add to the set of clauses U, and then I'll continue and basically repeat this over and over again. So I'll be deriving things, adding them to my set of clauses, and then doing this all over again until I'm actually able to derive something, derive what I wanted to derive, right? The goal, the target formula. In practice, a third thing can happen as well, and that's that I actually wasn't able to derive what I wanted to derive, but meanwhile I exhausted the computational resources, and then of course you can't go on and the thing breaks down. Okay, let's give an example here. Let's use resolution to prove that this is the case. So I'd like to prove that if I've got three premises here, A implies B, B implies C, and A, that this deductively entails C, right? And I can tell you this is the case since now if I would appeal to the natural deduction rules, A implies B, B implies C actually implies A implies C, and then by modus ponens, A and A implies C actually implies C, right? So yeah, this should actually work with resolution as well. Let's see if this is the case. First off, we need to convert all these three premises into clausal form. Now, not A implies B is equivalent to not A or B, and that's my first clause here. B implies C is equivalent to, well, not B implies C, and A is actually equivalent to the unit clause A. Okay, so no work here. Okay, so we got three clauses here, and now we can apply resolution. There's actually two ways we can go here. We could resolve A1 and 2 by basically resolving on B, and this would give me the rest from the first clause is not A, and the rest from the second clause is C. So this would give me not A or C, right? As the fourth clause, which I'm now adding to the set of clauses. The convention is whenever you apply a rule of inference, then next to it you leave a trace and tell us what you combined. So this was derived from clause 1 and 2. Okay, and once I've done this, now I can use this clause which I've just derived, clause number 4, and resolve with clause number 3 by essentially cancelling A, not A, and this leaves me C, and this is my fifth clause derived from 3 and 4. And that's exactly what I wanted to prove, right? C. So I was able to derive C as a deductive consequence of these three premises. The alternative derivation would be to, instead of combining 1 and 2, let me clean this up a bit. Instead of combining 1 and 2 as we've done here, to combine 1 and 3, right? So A and not A get cancelled. I'm left with B. That's going to be my fourth clause here. And then I can combine 2 and 4. 2 and 4, so it's not B and B, right? And this gives me the C, which is my fifth clause here. Again, same deductive consequence. So you see from this example that it can happen, and it's going to actually in real life happens quite often, that there is alternatives, there is alternative paths that we can take when we use resolution to prove something. And this then means that, you know, it can be that some of these paths are going to be promising, and in some of these we might get stuck, which makes proving via resolution actually a search problem, right? We need to find the best path, starting with from the set of premises and choosing, you know, whenever there is options on what to resolve, 1 or 2 or 1 and 3, choosing maybe the more promising step. This will motivate the introduction of proof strategies, where we look into a couple of simple ways how to make the proof more efficient. Okay, now there's one thing that we haven't been talking about. It's sort of an elephant in the room, and it's the completeness of resolution, right? Recall that there is two properties for a set of rules. First, we'd like the rules to be sound, which means that they derive what they derive is a logical consequence. But then we also like the rules to be complete, so that, you know, when something is a logical consequence, then we are able to use the rules to derive this as a deductive consequence. And, you know, the question is the resolution rule, and it's just a single rule, and that's a good thing, but, you know, still, is this single rule actually complete? So can we derive all logical consequences with a single rule of resolution? And it turns out, as the title of the slide suggests, it's not the case. Resolution is not complete. Okay, it is sound, but it is not complete. And this can actually be easily shown by coming up with an example where the resolution fails to derive something, although it should actually be able to derive it, because what it fails to derive is a logical consequence. Let's show this on this simple example. So I'd like to derive, starting from f as a single premise, I'd like to derive f for g as a deductive consequence, right? Now, I need to show two things here to convince you that the resolution is incomplete, that it can't do this, and it should, right? First, I need to show you that it cannot do this, and then I need to show you that it actually should be able to do this, because f or g is the logical consequence of f, right? So first, let's start with the first part. Let's show that the resolution cannot give me this, and that's actually quite easy. Okay, so can we actually derive this using resolution? No, we cannot. And, you know, that does it. That's the proof. Since resolution rule is not applicable to a single premise, right? It has to have two clauses as input. Remember that. It has to have two clauses. And here we only got one, so we can't do anything, and you know, we're done. And now the second part of the story is, does this actually hold, right? So is f for g actually the logical consequence of f? Well, you know, it does. And in order to show that this holds, formally you would need to construct a truth table, which would only have 4 rows, and it's trivial to do so. But let's skip this and instead rely on our intuition here. And, you know, if I have a formula f, then f or g will be true whenever f is true. I guess we would all agree on that without the truth table. So, you know, we are now in a position where we got this thing. So f or g is the semantic consequence of f, but we cannot derive this using resolution rule. And therefore it follows, as by as per definition of completeness, that resolution rule is not complete, since there is obviously logical consequences that it cannot derive. Okay, so that's the bad news, right? Resolutions seem to be so good. It's a single rule, it's sound, everything it needs can be converted to the form it needs, right? Any formula can be converted into clausal form. And the only thing where it fails is completeness, but it's actually quite a big failure, since now we are not able to prove all logical consequences, right? And this then brings us to a revised version of resolution for propositional logic called refutation resolution, which, as we'll see in a moment, turns out to be complete.